Hi, this is a video that's going to cover 6.1 in our textbook for AP Chem. And I'm going to go fairly quickly until I get to some of the calculations. So mainly I would recommend that you do the reading. So basically, energy is the ability to do work and to produce heat. And we know the law of conservation of energy, which really is saying that the energy in the universe is constant. It can only be changed from one form to another, never destroyed. It's also known as the first law of thermodynamics. All energy can really be classified as potential or kinetic. Potential energy is that energy that's stored in something, and then kinetic is any type of energy due to motion. We know that temperature is directly proportional, or kinetic energy is directly proportional to the Kelvin temperature of a substance. This is just showing you some of those conversions, like ball A on the left is definitely has potential energy, and then as it rolls down, it'll convert that into kinetic energy, transfer to ball B, and then ball A eventually stops. So heat and work are both ways of transferring energy. Heat is always transferring from temperatures that are high to temperatures that are lower. And work is a transfer of energy as force is acted over a distance. Pathway. So the pathway that some of these things like energy and work go through as they change. The pathway for energy is it's independent of the pathway, whereas work and heat are dependent on the pathway. What does that mean? What I'm really getting at are what we call state functions, and these are properties that don't depend on any of the in-between, really. They depend on the start and the end. So an analogy would be if you were hiking up a mountain, it doesn't matter as long as what route you take. It's where you started and then the elevation that you ended, and that would be the amount of elevation. So state functions, density, temperature, volume, those are some common state functions where it only really matters what the final and the initial values. Heat and work are non-state functions, so those have to be calculated. It's not just the difference of the two between two events. Heat and temperature are also sometimes confused. Temperature, remember, is that kinetic energy or motion of the particles measured in Celsius or Kelvin. Heat is energy, so that's going to be joules, kilojoules, cals, or kilocals. Energies, I already covered that. System and surroundings. So the system is whatever we're studying. The surroundings is everything else. So if we look at how energy, for example, this exothermic reaction here, this is the combustion of methane, which is what we burn in our furnaces in our homes. The energy here is being given off to the surroundings. So this would be an exothermic process. And if I tell you the delta H value is 100 kilojoules, we would say it's negative. So the negative means that the energy is given off during the process. So you can also look at the diagram down here, potential energy. So at the beginning, those reactants have a certain amount of energy, higher potential energy, and then at the end, the products still have potential energy, but less. So the drop here in the potential energy, we can also say that that's the enthalpy change, and it would be a negative value. So similarly, endothermic, so here's another reaction, but the energy is on the left side. This one, the energy has to go into the reactants for the reaction to happen. So delta H here, let's say it was 250 kilojoules, it's going to be positive. And that's because, again, you're starting with your reactants that have potential energy, you're ending with your product, and you're going up. You're increasing in potential energy. So this is a positive number. This is just a question thinking about if you were to start a fire with a match and kind of all the different energy conversions, endo, exo, system surroundings. There's a lot of different ways to look at this, but if you think of it starting with the match, if the match were the system, there's a little bit of an input with kinetic energy in striking the match, but then after that it's exothermic. So the energy from the match would go into the paper. So it's endothermic to the paper, but exo to the match. But then eventually the paper starts on fire and it will start to, emit energy into the air and into the log. So it really just depends on what part you're looking at. If you're looking at just the match, though, the potential energy of the unlit match is going to be higher than the potential energy after it's been burned, and then that difference is going to be the enthalpy change, which is negative. Here's another question. Is liquid water turning into ice? It is going to be exothermic because the energy, like if you put the water in the freezer, has to come out of it in order for it to turn into ice. So again, if I did a potential energy diagram, the liquid water has more potential energy than the solid ice. And it's kind of weird to think that it's exo, but so this is why sometimes people that are like have an orange grove, it doesn't normally freeze in those areas, but if there is a frost warning, sometimes they'll spray their plants with water so that the water, if it does freeze, will actually it will be exothermic, and therefore the energy will go into the plant and keep the plant from freezing. I'm going to go a little bit quicker here. So we're going to talk about internal energy. So this is just of a particular system that we're talking about. It's always the sum of the kinetic and potential energy of all the particles. And we're going to be using this equation. So the delta is the change in internal energy equals, so this would represent the kinetic energy and the work would represent the potential energy. So you're adding the Q value, which is also equal to delta H, assuming constant pressure. So how much energy is either absorbed or released during the process. And then work, I'm going to show you how to calculate work in a second. So when you have these numbers, like we've been talking about with the Q, the positives are always in terms of the system. So the positive means the system is going to increase in energy, and the negative means the system is going to decrease in energy. Work, like the physics definition, it does translate to chemistry, but we aren't going to be talking about pushing and pulling objects. We're going to be talking about gases. So a gas can do work on the surroundings, or the surroundings can do work on the gas when there's compression and expansion. This is kind of a summary of the values. So the work is going to be negative if the gas is expanding. It's going to be doing work on the surroundings, and work is positive if it doesn't have to be a gas either. It could be transitioning from a gas to a liquid, but if the substance is being compressed, then work is being done on it. So the classic here is just how our cars work in the cylinders. In the cylinders of our car, which have 4, 6, or 8, assuming we don't have a Tesla, there's a gasoline mixture with air, and the piston gets pushed down and compresses the air, so work is being done on the gas. So this would be a top positive work. And then you light it with the spark plug, and that causes the piston to rise. So this would be negative work. The piston moving up, so the gas is actually doing work on the surroundings. And that's what then turns into the mechanical energy of our wheels turning. So there's a derivation. But we're going to be using the equation right here. So work equals negative value of whatever the external pressure is that's causing the compression or resisting the expansion. Delta V is change in volume. It'll always be final, what you end with minus what you start with. And then there's this conversion, because when you use that equation, you're going to end up with a weird unit of liters, atmospheres. You can use this conversion to convert to joules, and then we know there's 1,000 joules in a kilojoule to go to kilojoule. So let's do this problem together. And you might want to try it, and then you can definitely pause the video and try working it and see how you do. I'm not going to pause the video, so I will start it right away. So I like to, when I'm doing these, think about what's going on. So I have an ideal gas. So I just have a gas in a container, and it is at 15 ATM, and it's occupying 10 liters. And we're going to allow it to expand. So it is going to, like if it were like a piston kind of holding it to that 10 liters, we now know that it's going to, have even more room. So maybe the piston now is up here. So our gas is the same gas there. And the external pressure that is working against it expanding is 2 ATM at a constant temperature. So we're going to calculate work in the unit of kilojoule for this expansion that's happening. So the gas is starting at 10 liters, expanding to a new volume. So what we're going to do is use Boyle's law, because temperature and the amount of the gas are constant. So I can say that P1 V1 equals P2 V2. So the one values would be what it started at, which was 15 ATM and 10 liters. And then it changes pressure to 2 atmospheres. And then we're going to solve for that new volume. So the new volume, if I do the math and solve for that, is going to be 75 liters. So the reason we're calculating the volume is because we want to be able to calculate delta V, which is the final minus the initial volume, so that I can then plug that into my work equation. So the final volume in this question is 75 liters. The initial is 10 liters. So my delta V is 65 liters. So now I can calculate work. I'll do that over here. Work is equal to the negative of the pressure that's acting against the expansion in this case, times delta V. So the pressure we're going to use is the 2 atmospheres. And then the change in volume that we just calculated, 65. So then when we do this, we get negative 130 liters atmosphere. And that's the unit now we're going to want to convert to kilojoule. So I know, I'm going to move some of this. Let me get this volume out of here. So I'm going to take the negative 130 liter atmosphere, and I'm going to multiply by that conversion factor that I gave you. 101.3 joules equals 1 liter atmosphere. And then I'm going to convert it into kilojoules. And you could do this last step just in your head if you wanted. But when I do this, I get a negative 13.2 kilojoules. So the gas is doing work on the surroundings. So we're getting a negative value. I'm going to do another couple problems, so we'll keep going. And the next one is, again, we're talking about a gas and a piston, so it could definitely change volume. And we're going to say as the system increases in volume, so we're going to start at a lower volume. So we have a piston, and we've got some gas. And the piston is going to work against a pressure of 0.5 atmospheres, and it is going to expand. So I'm going to end up with more room. So in this question, the system is going to absorb energy it's going to absorb 52.5 joules of energy from the surroundings. So that is going to be our Q value. So Q is positive 52.5 joules. And the piston is working against a pressure of 0.5 atm. So the outside pressure is 0.5 atm. And what else are they telling us? They're telling us that the internal energy of the system was decreased by 102.5. So delta E is going to equal 102.5 joules, and that would be positive. So, oh wait, 1 second. What was the... Oh, sorry, it's negative because it's decreased. So we know that delta E equals Q plus W. We know the value of the E. And we know the Q is 52.5. So really what we have to do here is calculate W first. So just the algebra here, I would get the work equals negative 155 joules. I'm going to change that back into liters atmospheres so that I can use the work equation, which is negative pressure delta V. So I know there's 101.3 joules in 1 liter atmosphere. So then that gives me negative 1.530 liters atmospheres. So I can plug that number in for my work over here. So negative 1.530 liters atmosphere. And that's going to equal negative, and then times the pressure that's acting against the piston, times the delta V. I know my final volume is 58 liters from the question, but I don't know my initial. So I'm going to solve for delta V. I'm going to do the algebra here. My delta V is 3.06 liters. So then I know delta V is the final minus the initial volume. So if I know the change in volume and I know it ended up at 58 liters, then I can solve for the initial. So the initial volume here is going to be 54.9 liters. So it was 54.9 liters. Energy was absorbed into it, and then it expanded into a volume of 58 liters, and that is how much that would be how much initial volume was in order for it to have an internal energy value of negative 102.5. So let's do another problem. So this one is, again, I like to draw pictures. So we have a mole of a gas, water. So it's a gas. It's going to be, it's at 1 atm, 100 degrees Celsius. And the volume now is 30.6 liters. And then it's going to condense. So energy is going to be coming out of it. And they're telling me that value of Q is 40.66 kilojoules. So I know that's coming out of the water for it to condense. So then I have 1 mole of liquid water. And I want to do, first thing I want to do is figure out what is this volume so I can get my delta V. So I can calculate the work. And then I can calculate the E. So ultimately, I want the internal energy, which is Q plus W. So I really need W. And in order to get W, I'm going to use the equation negative pressure delta V. and I need the second volume in order to calculate W. So what I'm going to do is do dimensional analysis. So I have 1 mole of liquid water, and I'm going to turn that into grams. And then I'm going to use density. So the density of water at this temperature, it's not exactly 1. It does vary with temperature. So there's 0.996 grams of water for every 1 milliliter of water. So you can write density as a conversion factor. And then I'm going to want to have my volume in liters because I'm going to be comparing it to the original volume, which was 30.6 liters. So you can just do this in your head or you can show it. When I do this, I get 0.0181 liters of liquid water. That's how much I have here. So I want to now calculate my delta V, sorry. So I'm going to take that final volume and subtract the initial volume. So I'm going to take 0.181 liter minus my initial volume, 30.6 liters. And I'm not really going to do sig figs right now because if I do, then you won't really see a volume change. So I just want to make sure that you see that it's changing. So when I do this, I get a value of negative 30.58 liters. And then I am going to now plug into the work equation. And my external pressure is 1 atm, given in the question. And then that delta V value. And when I calculate this, I do get a positive because the two negatives are going to cancel each other out and make a positive. And then I'm also going to convert now to kilojoule. So I'm going to use the conversion. 101.3 joules are in 1 liter atmosphere. And then I'm going to go 1,000 joules in a kilojoule. So I get 3.10 kilojoules of work were done on the gas to turn it into a liquid. So then now I'm finally ready to calculate the internal energy, which is the kinetic energy plus the potential energy. So the Q value, remember, it was an exothermic process, and the value was negative 40.66 kilojoules. And then the work is going to be a positive value. And then when I add those, I should get negative 37.6 kilojoule. So overall, the internal energy of this system is lower than what it was started by, 37.6 kilojoules. One more problem. This is just kind of review, but I wanted to show you one. So if we know the enthalpy change for a particular reaction, this one is delta H is negative 67 kilojoules. For every 1 mole of glucose that is turned into the fermentation of glucose to alcohol. I don't think I have the right reaction here. Let me just think. See, I'm going to pause the video and I will do this problem after I double check.